So good evening everyone. So welcome to my YouTube channel Maths Avtaram. So today we are going to see 7th lecture on uniform convergence. So today we'll learn a new test that is called Abel test to check uniform convergence of series of functions. Okay. So let's start today's lecture. Okay. So we are preparing a background to for a test to Abel test to check uniform convergence of series of functions. Okay. So we start with Abel's lemma. What is Abel's lemma? Okay. So Abel's lemma. Abel's lemma. Let Bn be monotonically decreasing sequence of non-negative real numbers. Real numbers. Non-negative means Bn cannot be negative. Okay, either it is 0 or positive. Okay. And the summation n goes to m2 p un is bounded below by small k and bounded above by capital K. For p goes to m, m plus 1, m plus 2 up to n. Okay. So, okay. So, then we have small k times bm less than equal to summation n goes to m2 p b n un is less than capital K times bm. Okay. For p is equal to m, m plus 1, m plus 2 up to n. So let's prove this lemma. Okay. Prove this lemma. So to prove this lemma, let's say SP is equal to summation n goes to m to p. Okay. un. Then what is this summation n goes to m p bn un. Okay, what is this? So I can expand this summation. What will be this? bm um bm plus 1 plus 1 bm plus 2 plus 2 up to bn un. Okay. Okay. So here is p. What is this? This is bp up. Okay. Now tell me what will be this? What? So bm. What is um? Um is nothing but sm. Okay. And what is this? What is this? Bm plus 1. So how can we write um plus 1? That is Sm plus 1 minus Sm. Okay. Plus. And what about this? Bm plus 2. Um plus 2 can be written as Sm plus 2 minus Sm plus 1. So Bm plus 2, Sm plus 2 minus Sm plus 1. So what is this? Bp? Sp minus Sp minus 1. So let's write it. So you see that I can take Sm common. From here it will be Bm minus Bm plus 1 Sm plus what will be this? Now if we take Sm plus 1 common, so it will be Bm plus 1 Bm plus 2 Sm plus 1. Okay. So what you will get next term? Bm plus 2 Bm plus 3 Sm plus 3. Okay. Sorry, 2 Sm2 Sm plus 2. Sorry. Okay. Sm plus 2. Okay. And so on. This will be, last one will be, so second last will be Sp minus 1. It will be here Bp minus 1 minus Bp, and last one will be Bp. Okay. Bp Sp. Sp. Okay. Last one will be this one. So now, so let's say is equation number 1. By by 1, we have, what we have? This one. We have this one. We have proved this from 1 that this is n goes to m2 p un, sorry, pm into un. Okay. So we have bn into un is equal to this bm minus bm plus 1 sm bm plus 1 bm plus 2 sm plus 1 bm plus 2 bm plus 3 sm plus 2. ये this is bp minus 1 minus bp sp minus 1 plus bp sp. Okay. Now you see that bp is bounded because sp is summation, and summation is bounded below by small k. So we can write small k in place of, then this summation will be less than, resultant thing will be less than, because sm is bounded below by k. So we are putting just k. So take K common. Bm minus Bm plus 1. Bm plus 1. Bm plus 2. Plus Bm plus 2. Bm plus 3. Bp minus 1. Bp plus Bp. So these two are cancel out. Okay. And this cancel out. And this similarly, this will be cancelled out from somewhere. And this will be also cancelled out from somewhere. And this is cancelled out. So what is term remaining? K times Bm. Okay. Okay. So what we got? We got K times Bm is less than equal to n goes to m to P Bn Un. Let's say it equation number. Again, by equation 1, we have what we have? We have, again you write equation number 1. What is that? N goes to m to Pn Un is Bm minus Bm plus 1, that is Sm. Bm plus 1 minus Bm plus 2, Sm plus 1 plus Bm plus 2 minus Bm plus 3, Sm plus 2, and so on. Bp minus 1 minus Bp, Sp minus 1 plus Bp, let's write correctly, plus Bp, Sp. Now Sp is bounded above by capital K. So if we put capital K in plus Sp, the summation will increase. So we have greater than equal to, Bm minus Bm plus 1 capital K plus Bm plus 1 minus Bm plus 2 capital K plus Bm plus 2 minus Bm plus 3 capital K, Bp minus 1 Bp capital K, Bp capital K. You take capital K outside, common. So what you have? K Bm minus Bm plus 1 plus Bm plus 1 minus Bm plus 2 plus Bm plus 2 minus Bm plus 3. Okay. Bp minus 1 minus Bp. Okay. Plus Bp. So this is cancel out. Sorry, Bm is cancel out. Sorry, one thing. Bm plus 1 is cancel out. So you see that Bm plus 1 is cancel out by Bm plus 1 here. Plus and Bm minus Bm plus is cancel out by this one. This will be cancelled out by somewhere from here. And this will be cancelled out somewhere from here. And finally this is cancelled out. So what is this? So this is capital K times Bm. So what does it mean? It means summation n goes to m to P Bn Un is less than K times Bm. From equation 2 and 3. from 2 and 3, we get from equation what we have, small k times bm is less than equal to k times and m goes to p, b and un, and that is less than equal to, from equation 3, capital K times bm. For p goes to m, m plus 1, m plus 2 up to n. So this is very important result we have proved, that is Abel's lemma. Okay. So what is Dirichlet test now? Dirichlet test. Sorry, this is not Dirichlet test. This is Abel's test. Sorry. What is Abel's test? Dirichlet test will come after Abel's test. So Abel's test. Okay. Abel's test for uniform convergence of series of functions. So what is this test? What is Abel's test? Abel's test. Let b and x, b and x from I to R be a sequence of non-negative functions. Okay. Such that b and x is monotonically decreasing for each x belongs to I. Okay. And there exists a small k greater than 0 such that b and x less than small k for all n belongs to n and x belongs to I. Okay. It means, what is the meaning of this? What is the meaning of this? Sorry. What is the meaning of this? The meaning of there exists k greater than 0. The meaning of this. What is the meaning of this statement? This up to this. This. The meaning of this is, I am writing in bracket. It means is that Bn is uniformly bounded on I. Okay. What is the meaning of uniformly bounded? There exists k greater than 0 such that Bnx is less than equal to, absolute value of Bnx is less than equal to k for all n belongs to n, x belongs to I. It means I is uniformly bounded. It means it is bounded independent you take n or x. Okay. So uniformly bounded. Okay. Now if n goes to 1 to infinity, u and x converge uniformly on I, uniformly on I, then summation n goes to 1 to n infinity. B and x, u and x also converges uniformly on I. Okay, on I. So let's see its proof. So we have B and X is uniformly bounded. It is given uniformly bounded on I. So what does it mean? It means that B and X is less than K times small k for all n belongs to n and X belongs to I. Okay. So we have, let's say equation number 4. Okay. Now, it is given that series this summation n goes to m to it is given that this series n goes to 1 to infinity u and x is uniformly convergent. Okay. So what does it mean? It means given epsilon greater than 0, every uniformly convergent series is uniformly Cauchy. So given any epsilon greater than 0, there exists capital N belongs to N and okay, there exists capital N belongs to N such that this partial sum. What is the partial sum of this? What we have this? Because uniformly Cauchy. So what does it mean? It means u n plus 1 x plus u n plus 2 x up to u n plus p x is less than epsilon by k for all n greater than equal to capital N and p greater than equal to 1. Okay. Or you can choose p. Okay. So you can choose p greater than equal to 1. So this series is uniformly convergent. So uniformly convergent series is uniformly Cauchy. And by definition of Cauchy, given any epsilon greater than 0, this will happen. Okay. Cauchy, because series is uniformly Cauchy. Okay. For all and X belongs to I. Okay. So this is happening. Now, how can we show that this series, how we can show that, I'm writing directly. So we are to show that our series converges uniformly. What series? We are to show this. we are to show, what we are to show? This series summation n goes to 1 to infinity b and x, u and x converges uniformly convergent. So uniformly convergent we are to show. But if we can show that this is uniformly Cauchy, still we are done. Because we have already proved that uniformly convergent series is uniformly Cauchy and uniformly Cauchy series is uniformly convergent. So we will show that this is uniformly Cauchy. So what we are to do? What we are to do? So what is this? Bn plus 1 x, un plus 1 x plus bn plus 2 x, un plus 2 x, u un plus, sorry, bn plus b I should write in. Bn plus p x, un plus p x. What will be this? So by Abel's lemma, what can we write? Because for a fixed x, we are taking here x fixed. So for a fixed x, so x is belonging to x is fixed, and for we know that Bn is monotonically decreasing non-negative sequence. So what we can say? So this will come out. So this will be bounded. This will be bounded by Bn plus 1 x. Okay, and what we have to take? Maximum of, okay, 2 goes to 1 to 3 up to p, u summation r goes to n plus 1 to n plus q. And okay, what is this? urx. But this is bounded by, okay. So what we are doing actually, how we are writing like this? So in Abel's lemma, we know by Abel's lemma this happens. A times small k times bm times summation n goes to m to p bn un. Okay, k times bn. So we can take maximum of absolute k and absolute k. Let's say it alpha. Then what will happen? What will happen? So we can write this by in the following: alpha times bm summation p bn un less than alpha bm. So it means what? It means what? It means what? So this will be less than n goes to m to p bn will be absolute value will be less than equal to alpha times bm. Okay, but this is true for p goes to m plus 1 up to n. So maximum will be less than this. So its maximum will be less than. Okay. So what does it mean? It means we can also write so what does it mean? We can take maximum. So we can write maximum Q goes to sorry P goes to M to N summation N goes P. Pn um is less than. Same thing is happening here. Same thing is happening. So that is why we are writing maximum here directly. Because no, this is going to be finite. So maximum is less than. So this is strictly less than k times. Okay. And this is strictly less than k times. This is less than equal to and strictly. So this is less than. Okay. For all x belongs to I and n belongs to capital N and p greater than equal to 1. So what does it mean? So this is epsilon. So this is strictly less than epsilon. So what does it mean? So write it in a proper way. So what we got? We got bn plus 1 x un plus 1 x bn plus 2 x un plus 2 x plus minus sorry up to so p n plus p un plus p x n is here is less than epsilon for all n greater than equal to capital N, p greater than and x belongs to I. So it means this series n goes to 1 to n dnx unx is uniformly Cauchy on I. So this is uniformly convergent. So this is the series unx is uniformly convergent on I. Okay. So we have proved this result. Okay. So let's see some examples on this theorem or test. Example number 1. So I am seeing this example. If n goes to 1 to n, an be a convergent series of non-negative terms. Okay. Then the series then n goes to 1 to infinity n to the power x is uniformly convergent on closed interval 0 to infinity. Okay. Okay. So let's see its proof. How it will work. Now you see that first of all this sequence is b and x you take 1 upon nx. So you see that this sequence 0 infinity to a non-negative sequence. This is non-negative sequence, and for fixed x, so b and x is non-negative for all n belongs to n and x belongs to 0 to infinity. Okay, and for each x belongs to I, 1 upon nx is monotonically decreasing. Okay, and you also see that this is uniformly bounded as well, because you take any, this is always for any n belongs to n, x belongs to closed interval 0 to n. This implies 1 upon nx, yani bnx is uniformly bounded. So bnx is non-negative sequence, it is uniformly bounded, and for fixed x belongs to I, it is monotonically decreasing. Now what about this series? Now this series is 1 upon n goes to 1 to a n. This is convergent series of non-negative terms. This is convergent series of non-negative terms. There is no axis involved, so automatically for all x it is convergent. It means it is uniformly convergent because it does not depend on x, and it is convergent. So it is uniformly convergent because it does not depend on x, so it is uniformly convergent. So by Abel's test we have summation n goes to 1 to infinity a n to the power x is uniformly convergent on closed interval 0 to infinity. Now see second example. You see this example. Is summation n goes to 1 to infinity minus 1 to the power n x to the absolute x to the power n uniformly convergent on okay. Now what about this solution? So your answer is yes, this is uniformly convergent. Why? You see this. So I will write like that. So you see that I will take bn. Now this is b and x is non-negative. Okay, because this is absolute value. And you take for each x in this range, for each x in this range, b and x is equal to is monotonically decreasing. Monotonically decreasing. Okay. Also x to the power n, because my x in this range, so it will not exceed for all n belongs to n and x in this range. So it means bn x is equal to x to the power n absolute value is uniformly bounded as well. Bounded. Now bnx satisfy all the conditions in Abel's test. Now what about my this series? N goes to 1 to infinity minus 1 to the power n. We know this is convergent series always. Convergent series of real numbers. So obviously x is not involved here, so it is uniformly convergent. Convergent in this range. Okay, because x is not depending in, but so it is automatically going to be uniformly convergent on this. Now by Abel's test, the series summation n goes to 1 to infinity minus 1 to the power n is uniformly convergent on this. Okay. So today what we have learned, we have seen Abel's lemma. Then we prove by help of Abel's lemma, we prove Abel's test for testing uniform convergence of series of functions. Okay. Now we have seen two examples. Okay. So we have seen how to apply Abel's test. So thank you very much for today's lecture. Kindly like, comment, share and subscribe my YouTube channel. If you have any problem, you can comment on my YouTube channel. We will see it in next class. Thank you very much for today's lecture. Thank you very much.